So today we'll be talking about something very interesting in relations. We'll be talking about certain kind of relations which are symmetric in nature. And within this, there are three important concepts. The three concepts are number one, symmetric. So we'll be understanding what are symmetric relations. And then we will try to understand the terminology anti-symmetric. And also there is another terminology, important concept of asymmetric. So these three things are something that we will be learning with this lecture. Let's start with symmetric. So we have been talking about relations, and previously we have spoken about a relation which is a relation of an element with itself that is reflexive. Now let's focus on each of these terminologies one by one. Symmetric. So we say that a relation is symmetric. By the word symmetric, what do we mean? That things would not change. The order will not change the relation as such. So that's the concept here. A relation R is said to be symmetric on a set A if, in case A comma B belongs to R, that means A is related to B, then B is also related to A. Then that means B comma A should also belong to this set R, the set of relations. So it doesn't matter whether we are writing A comma B or B comma A. Both these ordered pairs should be satisfying this relation. For example, let's say we are talking about not equal to. In numbers, say 1 is not equal to 2, 2 is also not equal to 1, right? So that's symmetric. In other words, it's a scenario like 1 comma 2 belongs to R. That should imply 2 comma 1 belongs to R. Suppose the relation was not equal to. So clearly 1 is not equal to 2, and that implies 2 is not equal to 1. So that means this relation not equal to is symmetric, because if I will deal with any natural number, any number out here, this relation will be satisfied. Now similarly, another terminology for it, the way we can write it is in a general manner, XRY should imply YRX, whatever relation R is. If this is happening, then the relation is said to be symmetric in nature. Let's take some examples. The first example I'm taking is the set relation R phi. I'm quoting it for the set phi. So suppose phi is the set of relation. That means it has no entries. It's a null set. Can we say this relation R phi is symmetric? This contains no entry. Now the statement that we have is that in case X R Y happens, then Y R X happens. Now for X or Y to happen, we need to have this entry X comma Y in this set. We don't have this entry. If we had this entry, then YRX should have happened, but we do not have any entry here. So by default, R phi is symmetric, because I cannot prove that it is not symmetric. Now let's take the set RA. I'm talking of RA as the Cartesian product, whatever set A you take, the Cartesian product of A with itself, A cross A. So that means it contains all possible ordered pairs, A comma B, such that A is from A and B is also from A. All possible combinations that you can make, you will find that in this set R. Will this relation be symmetric? So if I take a example like ABC, cross A consists of AA, AB, AC, then you will have combinations BA, BB, BC, then you will have combinations CA, CB, and CC. Now, our definition of symmetric relation means that if A are B, then B are A. In case A, B is here in the set, then BA has to be here in the set. And since A cross A consists of all the possible combinations of the elements that you have in A, That means our A is symmetric. Take A as the set of natural numbers. So I'm considering all natural numbers here. Now consider a relation R as the relation not equal to. The relation not equal to, and let's take our A as the entire set of natural numbers. So in natural numbers, if I take any particular natural number, say 1 is not equal to 2, and then of course 2 is also not equal to 1. And if you take any general natural number n1, n2, which are not equal to each other, then of course whether you have n1 not equal to n2 or n2 not equal to n1, it's the same thing. So n1, n2, in other words, belong to R is implying n2, n1 also belongs to R, which means this is a symmetric relation. Next example, let's take A as the set consisting of 4 numbers 1, 2, 3, 4. And let me create some relations. R is the set consisting of 1, 2, 2, 1, 3, 4, 4, 3. So is it a symmetric relation? Well, symmetric means that in case x are y, then y are x. So 1, 2 is there, 2, 1 is there. In case 3, 4 is there, then 4, 3 is also there. So which means that this is a symmetric relation. Let's now take the relation R dash as 1, 1, 1, 2, 4, 1, 3, 4. Now 1, 1 is here. So 1, 1 behaves like x, r, y. And since x is also 1, y is also 1, I can say y r x as well. So it's happening with 1, 1. But what about 1, 2? 1, 2 is an entry here. The ordered pair 1, 2 means 1 is related to 2. But I cannot see 2, 1, which means I cannot see in the set that 2 is related to 1. That means this is not a symmetric relation. Fun fact. If I take R as 1, 1, 2, 2, 3, 3, 4, 4, and then I ask you a question, is this relation R symmetric in nature? The answer is yes. For a simple reason, as I mentioned in the previous example, also 1, 1 is there. That means 1 is related to 1. And since both the entries are 1, so again, I can say 1 is related to 1, and this behaves like xry, and this behaves like yrx. The same thing happens with 2, 2, 3, 3, 4, 4. So if I consider each of them as general form xry, I do have yrx as well, because that's this ordered pair itself. So yes, this relation is symmetric. We have understood what is symmetric. So what is this term antisymmetric all about? Antisymmetric would mean that the relation or the set R, in case it consists of x, r, y, it should not consist of y, r, x. And if by any chance it consists of y, r, x, that is, it does consist of y, x, then x and y should be equal. R is said to be antisymmetric on a set A if A, B belongs to R and say B, A belongs to R. Then A should be equal to B. So antisymmetric is basically saying that in case A, B belongs to R, A is related to B. B can be related to A only when A is equal to B, not otherwise. If a relation set R consists of 1, 2 and 2, 1, that means it is symmetric if these are the only two entries here. But it is not antisymmetric. Why? 1 is not equal to 2. Therefore, it is not antisymmetric. Let us throw some more light on it using certain examples. Let's take R as the relation set consisting of 1, 2, 3, 4, 4, 4. So my question is this relation antisymmetric? Well, it consists of 1, 2. Does it contain 2, 1? It does not contain 2, 1. So I don't need to bother about 1, 2. It contains 3, 4. Does it contain 4, 3? it doesn't contain 4, 3. So I don't need to worry about 3, 4 as far as antisymmetric is concerned. It consists of 4, 4. Now it consists of 4, 4, which means that 4, 4 is 4R4. So this is like X R Y, and X and Y both are 4. So I can say YRX also, because that will also be 4, 4. So YRX is also present. But when 4, 4 is present, if I take it as XRY or YRX, so I can say that XRY is there and YRX is there. And the fact is, so because 4 is equal to 4, we do not have any problem with antisymmetric here. This is an antisymmetric relation because, number one, for antisymmetric, remember, in case A comma B is there, then B comma A should not be there only. Either that is happening. Otherwise, what should happen? In case B comma A is here in the relation set, then A should be equal to B. So 1 comma 2 is there, 2 comma 1 is not there. So no issues with this entry. 3 comma 4 is there, 4 comma 3 is not there. So no issue with this entry. 4 comma 4 is there, but 4 comma 4 in 4 comma 4, 4 is equal to 4. So therefore we have no issues. So this relation R is antisymmetric. 1 belongs to R, but 2, 1 does not belong to R. So there's nothing to check. 4, 4 belongs to R, 4, 4 belongs to R, and 4 is equal to 4. Therefore, this is an antisymmetric relation. Let's take some more example. And to understand how antisymmetric and symmetric are related to each other, let's understand that with an example. Can a relationship be both symmetric and antisymmetric at the same time? Let's take a general example. Let's take A, which consists of X, Y, and Z. So relation set R is the set consisting of all diagonal pairs XX, YY, and ZZ. Is R symmetric? We have just seen before this. Yes, it is symmetric. Because XRX, that is a symmetric relation since X and X are equal, right? Is this relation antisymmetric? So with the example of 4, 4, I think you must have understood by now that this relation is also antisymmetric. Why? Because XRX is happening, and since X and X, they're the same thing, if I take it the other way around XRX, then also, since X is equal to X, therefore it's an antisymmetric relation. So in case a relation is symmetric, it can be antisymmetric at the same time. Continuing with this concept, and let's talk about asymmetric relations. What are asymmetric relations? How are they different from symmetric and antisymmetric? Let's try to focus on that. Well, a relation R is said to be asymmetric on a set A if, what happens? If X comma Y belongs to R, then Y comma X should not belong to R. Let's compare asymmetric with antisymmetric. So antisymmetric means that if X comma Y belongs to R, that is X is related to Y and Y is also related to X, then X must be equal to Y. And asymmetric says that in case X is related to Y, that is X comma Y belongs to R, then Y comma X should not belong to R at all. So Y cannot be related to X. That's what asymmetric means. If I take the set of relation as 1 comma 1, 2 comma 4, 3 comma 2. Now what's happening here is you have 1 comma 1, which means that 1 is related with 1 and 1 is equal to 1. So if I take X and Y, in terms of X and Y, if I start thinking, so if this is X and this is Y, then X are Y and Y are X also, but X is equal to Y. So that means this is an antisymmetric relation as far as 1 comma 1 is concerned. Now, along with that, you have 2 comma 4 and 4 comma 2 is not there. So we don't have to bother about checking anything, because antisymmetric says that if you have x are y and y are x, then x and y should be equal. So y are x is not here only, so we don't have to worry. Similarly, 3, 2. 3, 2 is there, 2, 3 is not there only. So I don't have to worry about this not being antisymmetric. So this is an antisymmetric relation. Change this example a bit. So you have 1, 1, 2, 4, 3, 2. I'm keeping just like this, and I'm adding another ordered pair 4, 2. Now what's happening here in this relation is that you have 1, 1. We don't have any problem with 1, 1 as far as antisymmetric is concerned. With 2, 4, this time what is happening? I also have 4, 2. So 2, 4 is there. That means x are y, and y are x is also there. But x is not equal to y. So 2, 4 is there, 4, 2 is there, but 2 is not equal to 4, and that is why now this relation turns not antisymmetric. This relation is not antisymmetric. Similarly, I'll give you an example of, say, less than or equal to. Is less than or equal to a antisymmetric relation? Now, less than or equal to, if x is less than or equal to y and y is also less than or equal to x, suppose we have natural numbers, x and y belong to n, and x is less than or equal to y and y is less than or equal to x. This will only happen when x is equal to y. Otherwise, logically, it's not possible. This will only happen when x is equal to y, and hence this is an antisymmetric relation. This is what antisymmetric says, that if x are y and y are x, then x equals to y, and this will happen with less than or equal to. So strictly less than, if I may now ask you, is this an antisymmetric relation? The answer is yes. Why? Because 1 is less than 2, strictly less than 2. But actually 2 can never be strictly less than 1. In order for it to be an antisymmetric relation, it's an if and then condition. It's a conditional statement. X are y and y are x. If this is happening, then that should imply that x is equal to y. But honestly, in this relation strictly less than, y are x cannot happen at all. So this is a vacuously true condition which you cannot disprove, because the hypothesis is not happening. What is your hypothesis for this implication? The hypothesis is that x is related to y and y is related to x, but y is not related to x. So this is an antisymmetric relation. What is not an antisymmetric relation is being married. If the relation is being married, then that is not antisymmetric. Why? A is married to B, A are B. Then automatically B is also married to A. This is happening. But A and B are two different people. A and B are two different people. So this is not an antisymmetric relation. With this, now I'll give you some more examples of asymmetric. Now let's try to figure out whether strictly less than is asymmetric. Now strictly less than is asymmetric. Why? Because if you take any xy from the set of natural numbers, strictly less than is an asymmetric relation, because 1 is strictly less than 2. Then 2 is definitely not strictly less than 1. And that's a property that all the natural numbers will follow. So therefore, we will say that it is an asymmetric relation. Relation minus. And let's take the set of relation R as the set of all ordered pairs x, y, such that x minus y equals to 1. So clearly 2, 1 belongs to R, but 1, 2 does not belong to R for a simple reason. When you take the difference, 1 minus 2, you will get minus 1 and not 1. So therefore, this relation is asymmetric. But is this relation antisymmetric? Yes, this relation is antisymmetric also, because 1, 2 is not a part of R itself. So there's nothing to prove. is strictly less than antisymmetric. Strictly less than also, if 1 comma 2 belongs to R, that means 1 is strictly less than 2. 2 comma 1 does not belong to R. And therefore, we cannot disprove the fact. So therefore, it is antisymmetric as well. Now coming to that, tell me something. Do you think less than or equal to will be asymmetric? We've seen that it is antisymmetric. Will it be asymmetric? The thing is, the moment I take less than or equal to, then 1 comma 1 is a part of it. 2 comma 2 is also a part of it in terms of natural numbers. Therefore, this essentially means that if I take x r y as 1 comma 1, then y r x is also happening. So therefore, clearly, strictly less than is asymmetric and antisymmetric, but less than or equal to is antisymmetric, but it is not asymmetric. Well, please remember always, asymmetric is opposite of symmetric, clearly by definition, but it is not same as antisymmetric. Let me take some more examples to clarify symmetric, antisymmetric, and asymmetric relations. So let's take some relations R on the set A. A consists of 4 elements, 1, 2, 3, 4. And first example, R consists of the ordered pairs 1, 2, 2, 3, 3, 4. Is it symmetric, antisymmetric, asymmetric? Well, for symmetric, what do you require? If 1, 2 is there, then 2, 1 should be there. That's not happening because the next is 2, 3, 3, 4. So is it symmetric? Absolutely not. Is it antisymmetric? For antisymmetric, what do I require? That if 1, 2 and 2, 1 is there, then 1 should be equal to 2. But the fact is that 2, 1 is not here only. Similarly, 2, 3, 3, 2 is not here. 3, 4, 4, 3 is not here. So there's nothing to prove. So therefore, we can say that this is antisymmetric. And 1, 2 is there, but 2, 1 is not there. So therefore, it is asymmetric also because that's happening with each element that you have here. X, R, Y, but Y or X is not happening. So it's asymmetric as well. So what have we figured out? It is antisymmetric, asymmetric, but not symmetric. Let's take the same elements, except for I'm just adding another element, that is 2, 1. So you have 1, 2, 2, 3, 3, 4, and 2, 1. 1, 2 is there and 2, 1 is also there. So does it mean it is symmetric? Well, just for this pair. But what about 2, 3 and 3, 4? No, we don't have the opposite pairs. So therefore, it is not symmetric. Is it antisymmetric? Well, one counterexample is good enough. And the one counterexample that we have here is that 1, 2 is there and 2, 1 is there, but 1 is not equal to 2. So 1, 2 is there, 2, 1 is there, but 1 is not equal to 2. So therefore, it is not antisymmetric. Is it asymmetric? The moment in the set you have 1, 2 and 2, 1, it is not asymmetric anymore because the definition of asymmetric is that in case x are y, then y or x should not happen. If you take just the diagonal entries, what's going to happen? Is it a symmetric relation? Absolutely, yes, we've done that before. Is it an antisymmetric relation? Absolutely, yes, because what is happening is that x are y and y are x, and it both are happening. If you take 1 as x and 1 as y, so what is happening? X are y is happening and y are x is also happening. And that is implying that x is equal to y. It's only happening when x is equal to y. So therefore, it is antisymmetric as well. But is it symmetric? No, it's not symmetric at all because 1, 1 and 1, 1 could be taken the opposite pair as well. So that means x are y and y are x both are happening. So it's not asymmetric. If you take the set of all Cartesian products, all ordered pairs, then will it be a symmetric matrix? Absolutely, because all ordered pairs are there. So all opposite pairs will be there, right? Will it be antisymmetric? Well, you have 1, 1 You have 2 comma 2, you have 3 comma 3, you have 4 comma 4, and so on, and these were the 4 elements. Apart from that, you will have all other pairs also, 1 comma 2, 2 comma 1, so on and so forth. And because of that, let's just take the case of 1 comma 2 and 2 comma 1. So 1 comma 2 is there and 2 comma 1 is there, but 1 is not equal to 2. So that means it's not antisymmetric. And the moment you know that opposite pairs are there, x are y and y are x, it is not asymmetric as well. Right?